Okay, hello. This is going to be the first video for chapter 23, and we're going to be looking at some different types of optics with curved mirrors in this one. So the first thing I thought we should do definitely is pay a little bit more attention to ray diagrams. So we're going to see how you commonly draw ray diagrams um, when you're working with geometric optics. And we'll start with mirrors, and hopefully this won't change very much when we look at lenses and so forth and different types of objects that we're reflecting light rays into. So anyway, notice a common ray that you might want to draw is one that goes like parallel. So here we have an object. You can think of this as anything, but note that commonly we describe objects with an arrow so we know like which direction they're going if they get inverted and so forth after an image is produced. So anyway, we've got the arrow as an object, so this first ray that we commonly would like to do with all kinds of situations is just look at the top of that object and send a parallel ray from there into whatever type of mirror lens we have. So here we have a concave mirror, you can see it right there. So we have a ray going parallel into it, and if that's true, then that mirror is always going to direct that ray down through the focal point, wherever the focal point may be for this mirror. So we figured out the focal point for this one. Remember, for mirrors, whether they be concave or convex, the focal length is always just the radius of curvature divided by 2. So if we had the radius of curvature, if we looked at like a giant circle for this guy, and we found the center, like I don't know, it's somewhere over here, and we looked at that, that would be the radius of curvature. So this focal length right here is always going to be taking that radius divided by 2. So somehow you got to know the radius. Okay, let's see if I can get that junk out of the way. It always gets covered up down here. Okay, so let's just keep that in mind as we go. Okay, so the first ray is going to go down through the focal point. And notice, we can already see that the image is probably going to be inverted and over here somewhere. Okay, so another common ray, instead of sending one parallel through there, we just send one directly through the focal point. So that's what ray 2 does here, is it goes directly through the focal point. And if that's true, and we send it into the mirror surface, then the mirror is going to spit it out in a parallel fashion. So that's basically just like the opposite of what we did here. See what I mean? Okay, and then a third common ray that you might want to do is just from the top of that image, send a ray of light in a manner that intersects the mirror perpendicularly. So you say, okay, if I send it here, well, that's definitely not perpendicular. So you just try to make this be perpendicular to the mirror. I think that's always like the trickiest one to do, or one of the trickier ones. And if it's perfectly perpendicular, then of course the mirror is going to spit it back onto itself. So you send the ray out like this, and it's going to come back along itself. And then if you look at all three of those rays and look where they intersect, which is down here, you can see where the image is formed. So this one looks like it's formed on the same side as the object, but it's back here and it's inverted. Okay, so is that a real image? Is that a virtual image? Since I think that the eye can see it right here, I think if we held it up like a piece of paper at this location, there would be an image on that paper, so it would be a real image, not a virtual image this time. Okay, all right, so there's kind of the three common rays. Parallel, and it's going to go back through the focal point. Through the focal point, it's going to come back parallel, and then trying to find a perpendicular one that's going to bounce back in the exact same fashion. There's other ones you can do, but those are the common ones that we're going to use in this entire unit. Okay? All right, let's look at another. So I thought we should go through this derivation together. I didn't think it was necessarily the easiest derivation, so I thought we'd go through it together and then we'll look at some easier examples. Okay, so this is the tough part. So here we have that same situation as before. We can see that we have the image in the same spot, pretty much the same idea as before. And we're going to kind of up with the equation that describes distances. So we have the distance of the object right here. You can see that's like down here at the bottom. You have the distance all the way up to that image. That's right here down at the bottom. We're going to relate those distances to just the focal length of the mirror, so that if we know any two of these three, we can find the other one. Okay? And that's pretty easy to know, because if you know the dimensions of the mirror, you're going to know the focal length. And if you just put the object anywhere, you're going to know d sub 0, the distance to the object, so you can figure out how far away the image is. So that's pretty nice. So here's the derivation we're going to do. First, we're basically just going to be looking at similar triangles. So I'll highlight those in blue. So first, notice they've done one of, that's array 2 that we just did, isn't it? Where it goes through the focal length and it spits it back out parallel. Now they've added a fourth ray here, so this is a fourth ray that you could do an array diagram, any ray diagram we see this semester. And this one they just shot from the top of the object, directly at the middle of the mirror, and the law of reflection says, well, that's going to spit out at the same angle. Okay, so let's recall that the law of reflection says that it's always going to come off at the same angle then. Okay, so that's a fourth ray you could consider. I don't think it's as common as the others, but anyway, that's what they did. So they say first you can come up with this little relationship right here. Now why is that? Why is that? So let's look at the triangles in a little more depth. So I think they say to first examine this triangle right here. Okay, and we're going to compare that triangle to this bigger triangle right here. And the book argues that they're similar, so let's see if we believe that. Are they similar? So this is obviously a right angle, and that's obviously a right angle. That's good. They got two angles that are the same. Because of the law of reflection, don't we know that this angle right here and this angle right here, those are also equal? If you remember from geometry, there's all kinds of ways to say triangles are similar. You have SAS, ASA, there's no AS, if you remember. But there is AA for similarity if you just want triangles to be similar. So notice, since we have two pairs of angles that are congruent, these triangles are similar. And if you remember, there's a theorem that says corresponding parts of similar triangles aren't the same, but they're proportional. So I think that's what they did here. So H sub O is this guy, right? We've got H sub O. They said that compared to D sub O, which is like this length right here, is the same as H sub I compared to D sub I. Yeah, I think those are proportional if the triangles are similar. So that's what they said, okay? So that's how they came up with this little guy down here. All right, let's erase that stuff and start over with a new one. So next, I think they said observe O prime OF, this little triangle right here, and compare it to this triangle right here, not along the mirror, but along this perpendicular right there. Okay, so all the way down there. Okay, and they say those triangles are similar. That's even easier, I think, because once again, we've got some right angles. You can see those right there. And these angles are vertical, so they're the same. Once again, we have AA. So the triangles are similar. So they're saying, okay, once that's true, H sub O, which is right here, compared to D sub O minus F, what is that? So this is F, the focal length out to F. And D sub O is this distance. So I think they're talking about this guy right here. So H sub O compared to this guy is the same as, they're saying, the focal length, H sub I. H sub I is right here, so that's right here. Compared to this guy, those are definitely corresponding sides, so they are proportional since the triangles are similar. Okay, so that says this equals this. And then I think the final step is to say, hey, these both have H sub O over H sub I, so maybe we can put these parts equal to each other, and I think that's what they did down here. And then finally they just did some clever dividing and stuff. Let's see. Might have to move this guy up a bit. Okay, so let's see. So I think finally they said divide by D sub O. Let's do that. If we divide by D sub O on both sides here, we get the D sub O's to cancel there, so we get 1 over D sub I equals, those cancel right there, so it's going to be 1 minus, and those cancel right there, so it's going to be 1 minus 1. This one's going to have an F under it, isn't it? And this one's, the F's cancel, so it's going to have a D sub O under it. And then I think they just added that to the other side, and that's how they got the main equation. Okay? And then they also said there's another main equation, which is for magnification. They said the magnification is defined as the height of the image divided by the height of the original object. So that's pretty easy. So magnification is height of the image, that's h sub I, right, over height of the object that you started with. And if we look at our equations here, you can also determine magnification then if it's h sub I over h sub O. We can look at that right here and say, if we go d sub I over d sub O, that's another way to get magnification from this little equation right here. Okay, now the one thing the book makes a big distinction about, which I think is important, is they say that you've got to have a negative sign here. Now why is that? I think that's just a convention. It doesn't come out of the equations. So think about why is that? Well, what kind of image did we get here when we started? Let's erase up here. So if we look at our original object, this guy right here, the arrow had it facing, oh my gosh, that's terrible. Didn't the arrow have it facing up though? You can see the arrow is up there in brown. I'm going to make it green. So the arrow is up. Notice that even though it's a real image, the image got flipped over and was inverted. So I think that negative means that the image is inverted. And when we do convex lenses, and where sometimes the image might pop up over here, somewhere over on the other side of the mirror, there also might be some negatives that come into play in that one, so be careful of those negatives, okay? So maybe we'll see one in a second. Okay, let's do an example. All right, this one says an object is a diamond ring, and it is that big, so we'll consider that like a height, so maybe that's like the height of the object. It's located 20 centimeters from a concave mirror, so maybe we should just draw a quick sketch over here. So we've got a mirror, I guess I'll put that in blue, it's concave, so it goes this way. We've got an object, pretty short, but it's 20 centimeters from the mirror. Let's look at the focal length first. So it says the mirror's radius of curvature is 30 centimeters. So we cut that in half and we get the focal length. So like the focus F is out here at 15 centimeters. Okay? Looks like these are all in centimeters, so I'm just going to leave it like that instead of converting to meters. So we've got 15 centimeters for the focal length. The object is 20 centimeters, so it's out beyond that, isn't it? So let's put the object, I don't know, out there. So the object is going to be way, well, a little bit farther. So maybe like right here. There's that ring. It's really short. Okay, so I think that's the situation. We could do our ray diagram and go parallel, bounce, and then go through, bounce parallel, and then try to make it like be perpendicular. You know, it's going to be tough though. So let's just use the equation and not draw it this time, okay? But ray diagrams are really important. You'll see. They'll come back. Okay, so here's the equation. It says where is the image? Isn't that d sub I that we want to know? So I think we know the other stuff in here already. So how about 1 over d sub I equals the focal length we said was 15. And then if we subtract this to the other side, 1 over, how far did we put the object? 20 centimeters, 1 over 20. Put that in your calculator and you get, let's see, I'm just going to do it, 1 divided by 15 plus 1 divided by 20. I got 0.11, and if I round, 117. Okay, so I'm just going to say 1 over d sub I is that, so in other words, d sub I is 1 divided by that, however you want to do your algebra there. And I just kept it in my calculator till the end, so I got d sub I was 8.57 centimeters. Okay, so in other words, the image is, book got something different. Oh, you know what? I added when I did it. Weird. This shouldn't be that. Whoops. Let's redo that. Sorry. Yeah, you're supposed to subtract, so let's see. Aha! So it's 0.017. And when I inverted that, I got 60. We'll keep significant figures, so 60 centimeters. So the object is in front of the, since it's positive, that means it's not like behind the mirror, but it's back this way, like a long way, okay? So let's keep that in mind and let's do our magnification. Remember, magnification is going to tell us whether it's upright or inverted. So we're going to say that's going to be negative 60 divided by 20. So it looks like it's going to come out as negative 3. So this image is going to be magnified by 3 times, in other words, or 300%, however you want to read that. And since it's negative, that means it's going to be inverted. So it's just like that other one we saw. So it would be like way back here and be inverted over there. But it's magnified by 3 times, right? So it'd be like 3 times as tall as the original object. Okay, this is fun. Let's look at another one. So this time we're going to have a 1 centimeter object, whatever it is. I don't know, diamond ring, whatever. So that's the object. We're going to have a concave mirror again, so that same kind of situation. We're going to say it's located 10 centimeters in front, so we'll put it right there. The radius of curvature again is 30, so that means the focus is going to be 30 over 2 or 15, just like the last problem, so it's at 15. And that guy's in front of the focus this time. So once again, remember, you can always do your ray diagram to get an idea. Let's see, did this problem ask us to? Yeah, I think it did. It said to actually use a ray diagram. So let's use a ray diagram and see if we can get an idea of where this image is. So first, we're going to go straight in parallel. So we're going to go this way. And then it's going to spit us back out through the focus, right? So we're going to say, it's going to be really hard to do this, so it's going to be very approximate because I'm using the mouse. So parallel, okay, right there, and then that's going to go back through the focus, right? So I think if we extend this line out behind the mirror into like imaginary land, we get one of our rays. Okay. Then let's do another one. I kind of want to switch colors here. Maybe I better not. Okay, so then what else do we do? What else do we do? What's another ray? Can you remember? Don't we go like through the focus to the mirror? What was ray 2? Wasn't it like the focus to the top of the guy and then out to the mirror? I think that was another one that we needed to do. I think that's ray 2, so mine's bent a little bit, but anyway, so then since it went through the focus, remember that's going to spit it out in a parallel fashion, so then we've got this guy that we can use to go backwards. And really, we've already got an intersection there. We're just kind of like refining it and checking ourselves if we do a third ray or a ray 3, and that one's really the trickiest. You've got to have a nice drawing. So we're going to once again try to go through the top of the image. Remember, you always want to stick through that same point, or I guess you could go through the bottom, but that doesn't work as good. You have to stick whatever point. So I always just start at the top, and you won't have any issues. So anyway, now from the top up here, let's do this one in blue. We've got to think, how can we make this perpendicular to the mirror? So right there, it still looks like it's a little bit curved to me. So if we want to go perpendicular from this spot, isn't it going to be like this, maybe, something like that? And that means the ray is going to bounce backwards in reality, but now we can use that to kind of trace where it would have gone. And if I'd have done this perfectly right, we'd get like one nice triple intersection there. Remember, you can always just do 2 as a rough sketch, but you know, the AP test might have you sketch one of these, so kind of want to know how to do all 3 rays. And there's other ones you can draw too, but these are the main 3. Anyway, so that's where the image is located. So now we can say, hey, that's where the image is. So it looks like this time it turns out it's behind the mirror, and it looks like it is magnified. It is taller, but it's not inverted, so we should have a positive magnification when we come out with our result. So let's actually calculate it now and see what happens, see if it makes sense. Okay, so determine the position of magnification. Well, we think it's going to be a negative position and a positive magnification because it's not inverted. So let's see, so the position is d sub I, right? focal length we said is 15, and distance we said was 10. So let's do that. So I got 1 over the distance was negative 0.033 and then continuing. So if you go 1 divided by that, you get that the objects, or excuse me, the images, distance is negative 30 centimeters. So it's negative. That makes sense because it's behind the mirror. So I really kind of have a pretty terrible sketch, right? It should be like farther back there, but if this is 15, this should have been like farther. So just a sketch. But this distance really, if you did a very nice sketch, is 30 centimeters. Okay, magnification, let's hope it turns out positive. So it's going to though, right? Negative 30. And then over 10. It's really both probably want to put a, I think we have enough significant figures for that. So that's just going to be 3. My magnification looks pretty good. So that's good. And it's positive, which means it's upright. So good deal. All right, let's do one with a convex lens just to switch it up. So this time we have a convex mirror. This is kind of like the, I guess, the rear view mirror of a car. It's supposed to simulate that. So the radius of curvature is 16 meters this time, so really big. So the curvature on that car mirror that you see, if you look at it, it'll probably look like a plane mirror because the radius of curvature is so huge. So it's probably going to look kind of flat when you look into the mirror. But anyway, so there's an object, we're going to say 10 meters in front of the mirror. So that's kind of like the guy behind you. So like here's your car, if you will, and you've got the mirror here, and there's the guy behind you, that object. It's quite a ways behind you. Okay, so we're going to say yeah. I don't know why I have this negative 15 here. Weird. So we're supposed to determine the image location and magnification. So I think we can still use the same equation for a convex mirror. We can still use that same equation. Maybe we'll do a ray diagram and confirm it at the end, but I think that this guy, I think my sketch is really terrible, so I don't know if a ray diagram is going to be very nice, but we'll see if we have time. So we want to find d sub I again, so we're going to go like this. And the focal length, if the radius of curvature is 16, then it's going to be the same thing, divided by 2, so it's going to be 8 meters. So quite big. So there's the focal length of the mirror. So focal point is going to be like, since it's convex, the focal point is going to be like over here this time, at like 8 meters. But notice it's on the other side, so you can see that the focal length is on the other side, so really that should be negative, shouldn't it? No, I have negative 15 there, so let's get rid of that. Yuck. So the focal length is about right there. So it should be negative, you can see on this convex mirror. Anyway, so then we still have minus the distance to the object. The object's in front, so we're going to keep that positive, and we said 10 meters in front. So what is that going to be? 1 over d sub I. Let's try my calculator here. So 1 divided by negative 8, and then minus 1 divided by 10. So I got negative 0.225 point. So flip that. And you get that d sub I is negative, and it's 4.44 about, or meters this time, right? So the distance to the image is negative 4.4 meters, so the image is going to be over here. If that guy was this tall, then let's get this out of the way to the focal point. And since it's negative, this image is going to be pretty close over here. And negative means, which way is it going to be? We have to find the magnification before we can figure out if it's inverted or not. So let's do that first. So magnification, we said, is height over, oh, but we don't have the height this time, do we? It's height over height of image over height of the object, but we said that's also negative distance to the image over distance to the object. I think we're going to have to use that one because we don't know how high it is this time. So that's going to be negative 4.44, and the object's distance was positive 10, so that's going to turn out to be positive, and that's like 0.44, isn't it? So it's going to be smaller, so it's going to be smaller by like 44%. So, and since it's positive, I think it's going to be upright, isn't it? It's not going to be inverted since the magnification is positive. So it's going to be like right here at 4 point, that's 8. Remember we said that was 8 to the focal length. And it's going to be about right here and pretty short and upright. Okay, so there's another, hope you found this video